Now, on to question C. Explain how this curve could be used to determine the molarity of the acid and how this curve could be used to determine the dissociation constant Ka of the weak monoprotic acid. This curve could be used to determine the molarity of the acid by using the amount of NaOH added at the endpoint. Because the weak monoprotic 1H plus given off acid and the NaOH are at equilibrium here, there's a 1-to-1 mole ratio. Thus, moles of NaOH here equals moles of acid here. First, use the curve to determine what the volume of NaOH in the solution is at the endpoint. Using the known molarity and the fact that molarity equals moles over liters of solution, find the moles added. So you look right here and see the endpoint and then go down to milliliters added. Use this in the total volume of the solution to determine the molarity of the acid. The Ka, acid equilibrium K, can be determined by using the milliliters added at the equivalence point, dividing it by 2, so taking the milliliters here, dividing it by 2, and reading the pH there. This equals the negative log of the Ka or the pKa. If you didn't have a graph, you could use the NaOH added divided by 2, converted to moles, and so on to determine the H plus concentration at the half equivalence point. The negative log of the H plus concentration will equal the negative log of the Ka. So essentially the Ka is the H plus concentration at the half equivalence point. This asks you to apply a titration curve to find Ka and molarity of the acid. Pretty straightforward. Follow the directions here if there's math, but a more complicated scenario will be described in E. This question requires that you know about indicators, which give a visual sign during a titration that show the endpoint has been reached. Indicators are things like phenolphthalein that change color at a certain point to indicate a change in pH. Indicators change color between plus or minus 1 of its pKa, so you just have to find pKa and you can find the best one. These were simply found by taking the negative log of the Ka. If you know logarithmic rules, this is very easy. If not, just use a calculator. So which one of these changes pH closest to the equivalence point of the titration? Well, the equivalence point pH is about 8. If you look back on this graph right here, you can see that the endpoint is between 7 and 9. So I would say Cresol Red, because it changes color from pH 7 to pH 9. It looks easy, right? Well, it is. All you have to know that is any combination of a strong acid and a strong base, so HCl and NaOH, is going to neutralize at equilibrium. So you just draw a titration curve that starts low for a strong acid and ends high for a strong base and has its equivalence point where pH equals 7. I drew this lovely graph on Excel. You can see that the equivalence point is about 7 and high pH here for strong base and low pH here for the strong acid. So let's note these differences. The drastic change in pH is greater. It goes from very low to very high. The drastic change in pH happens very rapidly. The equivalence point is always pH equals 7 because this is neutralization. The initial pH is very low and the final pH is very high. And there we are.